Hello everyone, welcome to part 1 of Radioactivity and Nuclear Chemistry. This is Dr. Rhonda Kofelt of Calhoun Community College. And we are going to do the first part of this, which is going to basically cover what the particles look like, whether they're emitted or absorbed. And so throughout the chapter, you're going to learn the definitions of several things. We're going to do mass deficiency and nuclear binding energy. Also, we're going to balance nuclear equations, calculate half-lives, and then make sure that we understand the difference between nuclear fission and nuclear fusion. And so in part 1, we're going to identify radioactive particles. So radioactivity is the release of high-energy particles or radiation from the nucleus of an atom. So we've looked primarily at how the electrons are doing things previously. Now we're going to look at the nucleus itself. And so all those rules that we've been going by during this semester are out the door because when we're looking at the nucleus, we are not really going by the same rules. Atoms that eject particles or energy from their nucleus are referred to as being radioactive. And then these radioactive nuclei spontaneously decompose. So they are getting smaller, and we refer to that as decay or radioactive decay because radioactive nuclei are unstable. And so in order to get to that lower energy level, that more stable area, they're going to be emitting particles or radiation so that they get to a lower energy level. The parent nuclide is the nucleus that is decaying, and then the daughter nuclide is what is resulting from that. Anything that has 84 or more protons is considered to be radioactive. Radioactive rays can ionize matter. They cause uncharged matter to become charged. And so that's how we use a Geiger counter, which we'll talk about a little bit later, to measure how radioactive something is. These rays have high energy. They penetrate matter, and depending on what the particle is, they penetrate more and more, and they cause phosphorescent chemicals to glow. Every atom of an element has the same number of protons, as you remember, and we call that Z. And if they have different numbers of neutrons, we call them isotopes. Isotopes are identified by their mass number A, so you have mass over number and then the element. So mass number is equal to the number of protons plus neutrons, and you see the symbol as this. So we call the nucleus of an isotope the nuclide because it's going to do something, okay? Less than 10% of nuclides are non-radioactive. Most are radionuclides, okay? And each nuclide, as we said, is identified by element mass number. So if you have, boron 6 or whatever, it doesn't matter, you're going to see it written like that. We naturally have radioactivity going around all the time, and we can categorize that by what types of particles that they are using to decay. Rutherford, remember him way back? He actually discovered the 3 types of rays, alpha particles, beta particles, and gamma particles. Alpha particles have a +2 charge and a mass of 4, so they're kind of like a helium atom. Beta particles have a -1 and are negligible, and so they're kind of like an electron. And then gamma rays are not particles at all, but they're just a wave of light, so they're just on the electromagnetic energy. In addition, some of these unstable nuclei emit positrons, and positrons are a mind blower. For the first time, they are a positive electron. Whoa. So some unstable nuclei will undergo what we call electron capture, and that is they pull that into the nucleus, okay? So they pull the low energy electron into the nucleus. So these things are going to be doing some crazy stuff compared to what we've seen before. So I'm going to briefly go through the different types of particles. I have a chart at the end that gives you all the information to summarize this up. So an alpha particle, alpha, is basically a helium nucleus. Okay, it has 2 protons and 2 neutrons, and so it has a mass of 4 and a number of 2. So that's why we refer to it as a helium or an alpha particle. And what happens is that, for example, if you start out with U-238 and you degrade that by emitting an alpha particle, then you're left with thorium-234. Okay, and so that's because when this bottom number changes, okay, this is the most ionizing but least penetrating, so that means you can protect yourself with light cloth or paper or something from the ionization of this. When it loses an electron, the atomic number decreases by 2 and the mass number decreases by 4, as I showed you up here. And I'm going to show you how to account for that when we are balancing the equations later. A beta particle is like an electron, basically. And so when you emit a beta particle, you're going to actually gain in number. Okay, beta occurs because you have an unstable nucleus, and so it gets rid of that electron-like particle. It's 10 times more penetrating, and so you have to have some heavy cloth, a really heavy apron. Its atomic number will increase by 1, but its mass will stay the same. Gamma rays are high energy photons. Remember, like if you've watched Star Trek, photon torpedoes. With gamma emission, you don't have any particle changing. It's going to stay the same as what you started with, but it's giving off a huge amount of energy. The gamma rays don't ionize a whole lot, but they do penetrate, and so it requires lead or very thick cement to maintain those gamma rays. Usually when this happens is you've done something else, like you've gone through beta emission or something like that, and then you have this big punch of gamma ray to get rid of that excess energy. The remaining particles that are in the nucleus rearrange, but you don't change the number of them. A positron, this one's a fun one because it's a positive electron. It has a charge of +1. It doesn't have much mass at all. Some people call it an anti-electron. It's very similar to a beta particle as far as how they ionize and penetrate. It's formed when you eject the nucleus, you transmutate a proton to a neutron. When the atom loses the positron from the nucleus, its mass number stays the same, but its atomic number decreases by 1. So my example here was phosphorus 30. Phosphorus's number is 15. It goes down by 1 number, and so number defines what the element is, so that's why it changes into silicon. Electron capture is when you pull the electron into the nucleus. You don't emit anything because you've pulled something in there, but the atom does change because you rearrange the nucleus, and so because when the electrons come in, they're going to change up how the electrons are oriented around those protons in the nucleus, and it will eventually form a neutron. Okay, so it will add to one of the protons in there and form a neutron, and because of that it has decreased the atomic number by 1. So here's a summary table of all of these that I was just talking about, and like penetrating power, their mass, the charge on them, what we can identify them as, like an electron or a neutron or whatever. And then the symbols, and then how you would write them. Okay, so you have this to look back on when you're doing this. And remember, gamma ray doesn't have mass or charge or anything. It's just high energy. And I've got some, I wrote this down at the bottom because if you see it written, like if you got the arrow and you have a plus whatever alpha, like if you had this, that means that you're adding that to it. If you have minus alpha, that means you're emitting it or taking it away from the reactant. It's just, there's some shorthand things that you're going to see when we do the reactions. And that's all we have in identifying particles of radiation.